So this is homework number 22, and it's on page 595. There's a pink box, or it's actually salmon colored, but I can't bring myself to say it's salmon. It's a pink box, and there are 9 statements on it, and you are going to prove each one. Prove 1 through 9. We're going to do one of them in class, so you'll know what I mean by that. So, today...
That's all?
That's it. That's it. Because, like, this... I could just... We're going to take 2 days to go over this section. I could just blow through it, and I don't want to because this is so important. What we're doing today, it is so very important that I want to take my time. I really want us to take our time with this topic. What topic might that be? Something called vectors. Okay? So, here we go. We're going to start off talking about, let's imagine we have a bowling ball. This is a bowling ball. Or any kind of ball, whatever. And let's say that its mass is, I don't know, how about 10 kilograms? It's a very, very heavy bowling ball. So maybe it's something else. It's some other kind of ball. Okay? And the thing is, this quantity right here, it's what we call a scalar quantity. Now, scalars are usually real numbers, but really any field will work as a scalar. And I'm going to take a second to describe what a field is. This is totally unnecessary. You will not find this in your book. But it's worth talking about what a field is. A field is a set together with the operations addition and multiplication along with addition. There has to be an element in the field that serves as the additive identity. And by that I mean there's some number that you could add to any number, and it gives you back the original number. What would that be?
0.
0, okay? So 0 is the additive identity, okay? Along with that, every single element of this set has to have an additive inverse. That is some number that when you add it to that number, it gives you the additive identity. It's the inverse, the additive inverse. And in this case, if I pick some number A, what number would I add to it to give me 0? Negative A. Okay, so here we go. So right now, you might think, well, like whole numbers, right? Like 1, 2, or how about, well, we have to have 0 as well, because I just said we have to have that, and 3. Another thing that a field has is closure. That is, you take any elements of the set and apply one of these things, and you get another element of the set. So for instance, if I take 1 plus 2, I get 3, which is an element of the set. We're going and so on and so on. But you'll notice these guys don't have additive inverses. So we would have to include all the negatives to get my additive inverses. Okay? So right now, just as far as addition, the additive identity, and the additive inverse, this guy works. And we also have closure, right? If I take any 2 of these, let's say -1 and 3, add them together, I get 2. It's another element of the set. We're good to go. It has an additive. It has the additive identity. Every element has its additive inverse. Cool. And in fact, if that's all you have, what you have is not a field, but it's what's called a group. But we want more. We want more than just that. We want to be able to multiply these guys together and have closure, which we do. Take 1 times 2, it gives you 2. We're good. Take -1 times 3, you get -3. That's also one of them. That's good. it also has a multiplicative identity. Multiplicative identity. So that would be a number that when you multiply it by that number, it gives you the original number. And so you said what it is, the additive or the multiplicative identity is indeed 1. But it also has to have multiplicative inverses.
So the reciprocal.
So, yeah. So in other words, now we want something so that when you multiply it by this thing, you get the multiplicative identity, which would be 1. And in that case, you'd have to have 1 over a. And so now we've, by demanding this, we've kind of introduced addition. And you'll notice, like, by having the additive identity and additive inverse, we've kind of introduced subtraction. Here, now we're introducing division, but as you can see, this set is incomplete. We have you could multiply any of these guys together, it stays in the set, so it's closed under multiplication. You have the multiplicative identity, it's in there, but we don't have the multiplicative inverses for these guys. But if we add them in, we get a new set, which we call the rational numbers, right? We get all the ratios of these guys. And it turns out that the rational numbers, which we denote blackboard bold Q, like quotient, right? Then you have all of this. And the rational numbers is something we call a field. There are other fields. So one of them is the rational numbers. Another is the real numbers. Complex numbers they also form a field. Okay? So the thing is, we're going to be talking about vectors, and you're going to hear me say scalar a bunch of times. And I'm going to say, your book doesn't say this, but scalars have to be a field in order for it to work. It could be the field of rationals, it could be the field of reals, it could be, it could be the field of complex numbers. It could be a more exotic field. It turns out, you'll notice that each one of these that I've written up have infinitely many numbers in them. There are such things as finite fields as well. A finite set of numbers that has all of these properties. We call them finite fields. We will not be dealing with those, but just so you know, moving on into the future, that when we're talking about vectors, we're always talking about its underlying scalar field. This will become this will make more sense. But when I say scalar field, we're talking about any field, and in our class, and pretty much for a very long time, the only field you're going to care about when it comes to vectors are the real numbers. But just so you know, everything that we're talking about will work if instead of talking about real numbers, we're talking about, say, complex numbers. Or we're talking about just purely rational numbers and no reals, like you can't have any irrational numbers or something like that. That also works. Finite fields also work. So everything we're talking about today, when I talk about scalars, this one happens to be an integer, but it could have been, I could have chosen the square root of 3 kilograms if I wanted to, and it works. And so in this class, we will assume that all scalars are real numbers, though any field will work for vectors. But it does have to be a field in order for all the vector stuff to work out. So I'm sorry, I had to go into it. I'm going to get rid of all this field stuff because, again, it doesn't really matter, though I don't want you to get into your head that vectors have to be real valued, or the scalars with vectors have to be real valued, because they don't. All you have to have is a field. But putting all that aside, we're just going to restrict our conversation today and for the rest of this class to real numbers. So from now on, anytime I say scalar, you're thinking some real number value, a single real number value. Questions? Did that make sense?
Yeah.
I mean, kind of, right? Okay, so now here's the thing. Not all quantities that you describe can be described by a scalar. For instance, if I'm talking about the force of gravity acting on this ball, you may or may not know this, but that the force, I'm going to put a little g for gravity, the force of gravity, you might know that this is the mass times the acceleration. And if we're talking about gravity in particular, the acceleration is the acceleration of gravity, which we call g. And if you're using kilograms and meters and stuff like that, that works out to be something like 9.8 meters per second. And so this is the force of gravity, and so you might think, well, that's a scalar, because when I take mass, it's 10 times 9.8, and you get that the force of gravity acting on this ball, 10 kilograms, is 98 newtons. And you'd be right, but you'd be missing something very important. Is the direction of this force. Okay? This force of gravity operates in this direction, down towards the center of the Earth. And so, a vector is a quantity that has magnitude, size, and direction. And so all forces, pretty much all forces, are vector quantities. And we usually would draw that, if we're drawing this in a physics class, we would draw that with an arrow pointing in the direction, right? This is the direction of the force of gravity. And depending on our scale, we would draw it so long so that this is 98 units long. So that would be 98 newtons in that direction. Okay. Other things have magnitude and direction. So like velocity, right? If you're driving in your car up a hill, say, right? That's a terrible car. So you have the speed, which doesn't care about what direction you're going in. The speed itself is just, say, 50 miles per hour. But the velocity includes the direction, right? And so in this case, we're heading in that direction, and so we have an arrow showing the direction of motion at this instant. And yeah, it's going to change because the guy's going to come up and blah, 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 blah. But right here, his velocity is this, and I've drawn it so long that it corresponds to, I don't know, 50 miles per hour or whatever, right? So we've already been dealing with this for some time, but we haven't really discussed what this is and how to deal with vectors. So another thing I wanted to do is so let's say I have a ball and I throw it in a certain direction. Let's say I throw it at like 45 degrees this way, and I throw it at, let's say, 2 meters per second. I would draw this right here corresponding to 2 meters per second. But if I threw another ball at, say, 4 meters per second in the same direction, I would draw this twice as long to show that it's moving that much faster, 4 meters per second. And so the length of the vector is what we're talking about with magnitude. Okay? And yes, each one of these things are vectors. It's a quantity that has a magnitude, and in every case, a direction. Questions? Okay, because this is going to start off very abstract. What we're about to get into, this is going to be very abstract, and it's going to be hard to, trying to grab on to what we're talking about, it's going to be a little difficult. Stay with me, because once we get through the abstract stuff, we're going to make it very concrete. But in order to really do this justice, we have to go through the abstract stuff. Because as you'll see, there's a very small but distinct difference between vectors and something else that we've been working with for a long time. So here, let me, can I get rid of all this stuff? Yeah. Okay. All right, so vectors. It is a quantity that has both a magnitude and a direction. We draw little arrows to show the direction, and the length of the arrow corresponds to the magnitude. Okay? And so if you remember, like when we were talking about last year with complex numbers, we said they all have a direction or a modulus and an argument, right? Same kind of thing here, right? The modulus would be the magnitude, right? Or the length. And then argument would be the direction. Same kind of thing here. Okay. Now, here we go. It's going to be abstract for a minute. Just get ready. Let's say we have 2 points. And these could be points in space. We're not talking about the plane, and it could be any dimensional space that we're talking about. It could be 3-dimensional space. It could be 4-dimensional space. N-dimensional space. Technically, it could be infinite dimensional space, though things change a little bit when you have a vector in an infinite dimensional space. But right now, we're going to talk about just, we have some space.
What's that even?
Yeah. Right. Exactly. So let's say we have 2 points. Let's call one of them P and let's call the other one Q. Why P? Well, point because P, I guess, and Q is the next letter. So 2 points. And what we can do is this orients something, right? We could draw a line going from one to the other. And that arrow right there is going to show the direction of this. And so we could, in other words, 2 points in the space. Maybe the space is 2-dimensional like the board. Maybe I drew P here and I drew Q over here. And so we have a 3-dimensional space, right? So like P lives here and Q lives somewhere up here. I could draw that like that, right? Doesn't matter. The point is, given 2 points, those define a vector. Because we could go from one to the other. And yeah, we could go from the other to the one, just perfectly fine, that's fine. But, and we also, we named these as far, once you have a vector, obviously this side is different from that side. We call this side the tip, we call this side the tail. And it goes from tail to tip. That's the direction of motion or of whatever, force or whatever we're talking about. Your book, given 2 points, will write this vector like this. PQ with a little arrow over it like that. So that's the vector PQ. The magnitude of PQ, the length, it's all that means, it's just the length, but the magnitude of the vector PQ is denoted 2 bars like that. You put whatever the name of the vector is in. 2 bars like that. And it's just the length. It's just the length. Okay? Now, this is where this is different from other things that we've talked about before. 2 vectors are equivalent. That means they're exactly the same thing if they have the same direction and magnitude. Doesn't matter where they are. So if I draw one like this, I'm going to pretend that they're exactly the same length and going in exactly the same direction. And let's say I give this vector a name. Let's say I just call it U. And here's the thing. Okay, whenever you write down a vector, you write down a vector's name, you put a little arrow over it to denote this is a vector. So earlier, I didn't want to show my hand quite that soon, but the force of gravity, I should have put a little arrow over the top of it. Because that's what we do. That's the convention. Now your book, and every book I've ever seen, instead of doing that, what they do is they just make it bold. But good luck trying to make it bold. Like, it's going to look terrible. So everybody at some point just decided, you know what, when we write these down, in the book it looks okay because you could see a bold in the book. But we could never write it like that. So everybody just decided, you know what, we'll put little arrows over it. And that's what we do, okay? So we have a vector U. It has the same direction and the same magnitude. We're going to pretend that those 2 things are true. It's in a different place. And I'm going to draw another one. Maybe it's like this. The vector V. same magnitude, same direction, we're going to say that the vector PQ is equal to the vector V, and that is equal indeed to the vector U. They are equivalent. There's no difference. So in other words, if you have a vector somewhere in space, you could take it and move it anywhere in the space, and it stays the same vector. So if you have two vectors in two different places, but they have the same direction and same magnitude, then they are equal. Now the thing is, we're not going to use this very much. This is what makes a vector distinct from other things that we've talked about in mathematics up until this point. And it is a good distinction to know, although in practice we're rarely going to use this fact. But it is something very important that distinguishes vectors from other things. That they don't necessarily care about coordinates or where they are. The only thing that matters for a vector is its magnitude and direction. And all vectors, no matter where they are, that have the same magnitude and direction are the same thing. We're going to pretend they're the same. It's kind of like saying all even numbers are the same and all odd numbers are the same. So we'd say like 3 is the exact same thing as 5 and the exact same thing as 13. And 0 is the same thing as 4. You're just kind of, it's called an equivalence class. We're saying that all the vectors out there that have the same magnitude and direction, we're going to pretend they're all the same thing. Kind of instances of the same thing. Reflections of one true vector that has that magnitude and direction. That's kind of what's going on here. So that's the weird thing about it. Like that's the weird thing that sets vectors apart from other things, really. But we're not going to go really into that very much. Okay, so check this out. Cool thing about vectors, one of the cool things, well, I already said that they describe something that has two different quantities all in one fell swoop. And that's great when it comes especially to force. And so let's think about, say I have a tennis ball. I'm going to take this tennis ball and I'm going to drop it. And at that instant that I drop it, let's say that there's two things going on. Well, one, of course, the force of gravity is working on this tennis ball. And it has a certain magnitude based on the weight of the tennis ball, or the mass of the tennis ball, and a direction, which we're going to pretend is straight down towards the center of the earth. And so it has this force acting on it, the force of gravity. And I'm going to put a little arrow over it, because that's the vector. But let's say at the same time, when I drop this ball, there's wind blowing. And let's say that there's wind blowing in, say, like this direction. And it's not that strong, so I'm not going to draw it very long. I'm just going to maybe draw like that. And I'm going to call this vector F little sub W for the force of the wind. Okay? Now what we can do is say, well, what's the net force, or the resulting force of both of these things acting on this ball at one time? Okay, and that's actually, I'm going to go ahead and put that up here. Net force, something you need to know. Net force. That's all forces. The sum, or the, did I call it the sum? We'll just call it all forces acting on an object. So the net force here would be what we get when we account for both of these. Cool thing about vectors, like I said, we can move them around and they don't matter, right? So we could pretend that the ball is here, and we could say, well, there's this force, which is the force of gravity acting on it, F sub g. And from there we could say, and like the wind is going to act like this. There's the force of the wind. And so the resulting force, or in this case the net force, It's a triangle. Go figure. This would be the net force. Force N for net. Right there. This is also when you take two vectors and add, what we're actually doing is adding vectors. And you'll notice that I've added them tip to tail. I take one, move down, and then on that tip, I add the tail of the next one, and we get to here. And it's the same thing, and you can imagine this, right? Like the ball's going to drop like this, but the wind is kind of pushing up against it a little bit, so it's not going to fall as fast as it would, so that should be shortened a little bit, right? And that's what we're seeing with the upward amount. But also the wind is blowing it in this direction, so it's not going to fall straight down. So the resulting force, or the resultant, we could pretend that the sum of all those forces, this right here is what the ball actually feels. And this is how we could predict which way the ball is going to go and how fast it's going to go in that direction. Because the length of it corresponds to the speed, the direction of it corresponds to where it's going to fall. Does all that make sense? Okay? So what I've just done here, what I've just said is that the net force, I wrote it out there and put it in that, so we'll do it there. The net force is equal to the force of gravity plus the force of the wind. And in this way, we could add vectors together. You start somewhere, doesn't matter, and then you go from tail to tip, and then you put tip to tail, right? And this is how you add vectors, and this is the vector that you get out of that. Again, this is all very abstract right now, and it kind of has to be, because technically vectors, like I said, don't exist anywhere. There's no coordinate system here, right? Once you impose a coordinate system, then things get very concrete and very easy to deal with. But technically, vectors don't have a coordinate system, so we have to go through this kind of stuff. But anyway, that's called your resultant force, okay? Or the resultant. Since we're talking about forces, that's the resultant force. Now, here's the thing. It's not like the ball dropped and then the wind blew it, right? Like, I did it in this one and then that one, but I didn't necessarily need to do it in that order, right? Like, I could just have easily have said, well, we could do the wind first and then do gravity, right? Right here. And you would have ended up at the same place. Right? Yeah. Right? And so let's just take a look at this. This is the force of the wind. That's the force of gravity. This is the force of gravity. This is the force of the wind. Right? Now, we could have done this abstractly. We could have said, okay, here's a point P. Here's a point Q. Here's a point R. Here's a point S. Right there. And we could say, okay, here's a vector. And using the book's idea here, that's the vector PQ. This would be the vector QS. And it may not look like it, but I've drawn these the same size. So on one hand, this is the vector PR. But what did I say about vectors? Anyone that's in the same direction and is the same length is exactly the same as the other one. So this is the exact same thing as QS right here. Right? Like, that's the same. Kind of like I was saying, here's the force of gravity, that's the force of gravity, here's the force of the wind, there's the force of the wind. They're the same thing, because it doesn't matter where they are. So in other words, I'm saying QS is also equal to PR. Am I going too fast? Is everybody getting this? Yeah. It's just kind of, again, we're still in abstract land, and so this is kind of annoying. But RS, there's RS. But that's exactly the same thing as PQ. Okay, so they're the same thing. And then, okay, so if we go here and then go there, we have PQ, the vector PQ, plus QS. And it gives you, I guess we'll call this the vector PS. You end up at the same place you would have been if you had just gone directly from here to here, right? Everybody with me on that?
Yeah.
So I could go from there to there, or I could just go straight there, and it's the same thing. So in other words, PQ plus QS is equal to PS. But I could have gone this way first and then this way, and I would have ended up at the same place. So in other words, PS is equal to QS, notice, right? This is the same vector, QS, plus, then we could call it RS, but it's the same thing as PQ, so there's PQ. So in other words, it doesn't matter which order you do it, right? What did I just write here? Basically, Z x plus y, but Z is still equal to y plus x. In other words, addition of vectors is commutative. You could do it in either order, just like you expect from addition of numbers, right? 2 plus 3 is the same thing as 3 plus 2. Same thing is true for vectors. One vector plus another one works in both orders. Everybody with me?
Yeah. Yep.
Okay. Okay. So it's about to get concrete. Just stick with me for another minute. Just another minute, and then we're gonna pull all this together. Just need to get a few facts about vectors in the abstract out there first. And then we can actually start doing some. And again, I don't want to blow through this because this is so foundational for everything else you're going to do in math and physics and everything, that it's worth it to just take our time and really drive these points home. Okay, so let's let M be a scalar. Okay, so in other words, in our class we're going to treat scalars as real numbers. So M is some scalar. Okay, it is not a vector quantity, it is just a scalar. And this might suggest why we call it a scalar. I don't know for certain. I'm not sure. And let's let V be a vector. Okay. Then, now this is one thing that you could do with vectors. You could multiply a vector by a scalar and you get another vector. In other words, if I take M and multiply it by V, I get a vector. Let's call it U. Okay? And its magnitude, so this is the statement. Let M be a scalar and V be a vector. Then M times V is a vector, we're going to call it U. And the magnitude of U is equal to M times the magnitude of V. And the direction is the same. Okay? So, graphically, oh, I'm sorry. The direction is the same if M is positive and the direction is opposite if M is negative. So I'm going to do this all in one fell swoop. So check this out. Here's your visual. It's starting to get a little bit more concrete because now I'm going to draw a vector V. I'm going to have different M's that I'm going to use. Let's how about M is 2? If M is 2, then what that does is it basically stretches this guy out. Oh, I wanted specifically 2 times V. What it does is it just makes it twice as long, right? Because that's what that means. It's whatever m is times the magnitude goes in the same direction. Okay? Let's get another color. Let's go -1/2. This would be -1/2 v right here. In other words, the scalar scales the vector. I don't know if that's why it's called that. I don't know. But how can it not, right? Like, this is what you're doing. You take a real number, multiply it by v, and it either stretches it out, or it compresses it, or it might flip it around, right? So like -1 times v would be the same length, but in the opposite direction. And -1 times v, we'll just call it -v. Does that make sense? Yeah. Just call it -v. Okay, so, and we call this a scalar multiple of v. And so mv is we call it scalar multiple of v. All right. Now let's make this concrete. Everybody with me? Any questions about any of this?
So negatives just flip a vector like a graph?
Yeah, exactly. Exactly. It just flips it in the opposite direction. And we'll see that in just a second. Like when we make this concrete, this will be good. Okay. So, in our class, we are going to be talking about vectors in the xy plane. Okay? And like I said before, they could be in any space. Okay? It could be three-dimensional, could be many-dimensional. Doesn't necessarily need to be the xy plane, but in our class, all of our vectors will be in the xy plane. Okay? So, let's talk about a vector in the xy plane. So here's the xy plane. We'll do an x here and a y here. And let's just take 2 points, P and Q. And let's take the vector from P to Q. Keep this in black. So we've been calling this guy PQ with a little arrow over it. So that's vector PQ. And you know, there's lots of other ones that are equivalent to it. Anything that's in this, that's this length and in the same direction, so this vector right here, maybe we'll call him U. U is exactly the same thing as PQ. They are the same vector. Okay, different instances of the same vector, but they're the same thing. And so it's like, well, you know, we could standardize all these vectors. So you take any vector that's floating out in your space, and you just say, you know what? We're going to take your tail and put it right here. And let's give it a new name. Let's just call it A. There's the vector A. Okay. Now check this out. A goes from the origin to some point. Not sure what point that is. Let's just call it, how about A1 and A2? Okay, so the vector A goes from the origin, at 0, 0, to some point, whatever it happens to be, right? It depends on how far I drew it, how big that is, whatever. To some point, call it A1, comma, A2. Everybody with me on that? Anybody want to argue that that's not true? Any vector, you take it, drag its tail, then its tip is going to hit some point on the plane.
Yeah, can't really argue.
Yeah, it's, I mean, right? It's just, it's pretty okay. So then, every vector determines an ordered pair, which is a point in the plane. Yeah? There's two real numbers. We call these are the coordinates of that pair right there. Okay. But then again, every ordered pair Let's just give me any ordered pair. You think of any number, and you tell me what it is. I'm going to say, okay, I'm going to label it B1. Then you say, give me another number, and you say something. And I go, okay, well, let's call it B2. And maybe it ended up to be like over here. So here's B1, and here's B2. Well, that ordered pair determines one and only one vector that goes from the origin to that point. And in fact, we could call it, if we wanted to, we'd give it a name, about B. Right? So in other words, what I'm saying here is there is a one-to-one correspondence between points on the plane and vectors. Just as long as you take your vector and, because we said all vectors are equivalent, right? So it's kind of like we have infinitely many vectors that are in this direction, but we're going to say, you know what? Let's just choose of all of you infinitely many vectors. We're going to choose one representative vector. This vector right here represents all of you other guys. And so we could forget about all those other guys. And we're going to. And from now on, when I say the vector, and I tell you what it is, you're going to imagine some tail coming out of the origin out to some tip. Conversely, if I give you any point on the plane, you could say, well, that's a vector, really, because there's, no matter where it lives, you could draw a line from the origin out to that point, and that defines a vector. So in a sense, vectors are points. They're kind of the same thing. The only thing the vectors have that points don't have is this weird property that you could move them anywhere and they stay exactly the same. But in practice, we're just talking about points here. Like, there's no difference, really. But we'll see in a little bit, probably, if not next time, the time after, we'll see why it's useful to say, well, you could slide them around and they stay the same. That's cool. But really, when you're talking about vectors, you're talking about points. Okay? But to avoid confusion here, instead of writing the points like this, like we normally do with these curved brackets, when we're talking about the vector itself, we're going to use these pointy brackets. Call them pointy brackets. Okay? So we could say then the vector B is this thing right here. It's its coordinates. And so we know that we're not talking about a point, that we're talking explicitly about a vector, we're going to use these. Now, just as an aside, there's a lot of ways that this book uses these. Sometimes there are books that will use soft brackets to denote a vector. There are books that use column vectors. These are called row vectors. These are called column vectors. Does that sound familiar? Yeah. To anybody? Columns and rows, remember? Yeah. When you take linear algebra and you're learning what matrices do, you're going to be dealing with vectors like this. Basically, a matrix acts on a vector. Kind of cool. You can also see, they'll also be used like this. Some books will use brackets like that. Some will use brackets like this. They all mean the same thing.
What about the curly one?
Not curly braces. But these are 4 ways you could see a vector. This is another way you could see a vector. This is the way the book chose to do it. So from now on, this is how we're going to do it. Okay? Everybody with me? Okay. So as you can see, now we're making things concrete. We're no longer off in la la land. What we're talking about are little arrows that stick out of the origin and hit a point, and whatever point they hit, those 2 coordinates are what we put inside there, and we call that our vector. Okay? So, these are called the components of the vector. Okay, so these are the components. And if we were in 3 dimensions, okay, so we'd have some components here. We would have, say, C1, and maybe that's C2, and maybe C3 lives up there. And so the vector that goes from the origin up to that point right there, we would call it whatever number that is, whatever number that is, whatever number that is, and it moves up into higher dimensions in the same way. Since we're only dealing with 2 dimensions, we're going to chop that guy off, and we're just working in 2 dimensions. But everything we're talking about, everything that we're talking about will work no matter how many of these things you have. But you're just talking about adding another axis in there. Cool? Okay, so the entries in there are called components. Since we're doing things in R2, since art vectors live in R2, what do I mean by that? R, right? The real numbers. I'm talking about blackboard bold R here. And 2, the number of dimensions that we have. So earlier I wrote let M be in R, meaning that it's a scalar. I could have written let V be in R2. And so you know that it's a 2-dimensional vector whose components are real numbers. And you'll notice that the scalar field matches with that's why it's called this vector, its scalar field. The entries, the components of the vector are in the same field as what you're multiplying it by. Okay. A lot of nitpicking today, but it's important stuff. It is important stuff to know. Okay, so the magnitude of the vector. The magnitude of, we'll say, B is written B, which means the same thing as, which we could have written like this, B1, comma B2. Means exactly the same thing. And it's just the length. How do I find the length of that? What would it be?
Wait. Oh. The square root of B1 squared plus B2 squared.
There you go. That's it, right? It's just the Pythagorean theorem, right? It's literally the length. The magnitude is just the length. It's that easy, okay? And you can see this is a nice little right triangle. That's the great thing about using Cartesian coordinates, is that it makes this so simple. Ditto with 3 dimensions. If it were somewhere in R3, then its magnitude would be, you would just add a plus B3 squared and keep the square root. And it wouldn't be a third root, it would be a square root still. It's just by convention, that's what we do. Cool? Okay. Easy enough. It's just the length. The magnitude is just the length. The magnitude, it's just the length. Okay? Everybody with me on that? Okay. So, why didn't I write that? Oh, I did write it down. Okay, good. Okay, we're getting rid of this, and we're going to actually do some stuff. I kept saying, like, it's going to get less abstract, less abstract. This is still kind of abstract, because we're just talking about B's and A's and stuff like that. So let's get some actual numbers in here and work with actual numbers. Okay. Okay. So, I want to sketch the vector u, which is -1, 2, and find the magnitude. Okay, so we need coordinates. There's X, there's Y. And let's do U in blue. So U is in blue, okay? So -1, 2, this is just the point, -1, 2, It's not hard to do, right? There's minus 1. If that's 1, then maybe that's 2. Yeah, that looks right. And it's just the line segment that goes from the origin up to that point. Just like that. So there's my vector u. I'm going to label it u. Just like that. Okay? Now, let's see. We have another one. We're going to do the same. Oh, we didn't find its magnitude. What's its magnitude?
Root 5.
I believe so. Let's double check. So, the magnitude of u is equal to the magnitude of negative 1 comma 2, which is just, by definition, the distance. Negative 1 squared plus 2 squared is 1 plus 4 root 5. Yes. Nice. Okay. Now, let's do another vector. Same deal. We're going to sketch v. And v is going to be 2 comma 3. Okay, so let's sketch it. 2 should be about here. 3 is probably right around here. So there's 2, 3. There's the point 2, 3, and there's the vector 2, 3. Okay. Now, check this out. Remember how I said we could add vectors? We add them tip to tail, right? So what I could do, let's say I want to find the vector, let's call it W. And W is going to be u plus v. Really going all out for my color coordination today. Okay, so we can start with either one. Let's start with u first. And we'll go, we're starting at the origin, and we're going to go u up to here. And now, from here, we go from tail to tip. Now, tip to tail, right? We're at the tip of u. Now we draw the tail of v. And it should be something like this, right about there. So there's v. And we end up at this point, right there. We could have done it the other way, right? We could have said, well, do v first, because remember, these commute. It doesn't matter which order you do it in. We could have started at v and done v, and then we do u. And guess what? I would have ended up at the same place. Right there. And in both cases, we end up in the same place, and that point right there defines a vector. We're going to call it W. And it's what you would get, right? Because like I said, every point defines a vector whose tail is at the origin. Well, this is the vector, W, right here.
Isn't the one in blue be u?
Yes, thank you, thank you, thank you, thank you. And you'll notice what we've made here is a parallelogram. And any time you add two vectors together, you could do so using the parallelogram law, where you just make this kind of thing, right? You have your two vectors, and then you do the slide thing like that, and then the diagonal of the parallelogram is your resultant vector. Okay? But that's a pain, because what point is that? like, hopefully I did it right. I don't know. So this is the great thing about this is the rules. The rules for adding vectors. So u is -1, 2, plus 2, 3. The rules is that you just add components. The first component adds to the first component. The second component adds to the second component. And what we get, I'm going to be explicit about that, -1 plus 2, 1 plus 2, 2 plus 3, 2 plus 3, works out to 1, 5, I believe. Is that right? Yeah. And so there's your point right there, 1, And so W is the vector 1, 5. Okay.
Find magnitude.
So what?
Do we have to find a magnitude?
No, yeah, we could, but you know, the square root 26.
Yeah.
So yeah, so in general, and we're going to do this forever, and you're going to do this in your homework. If you have a vector A, you're going to rewrite it as A1, comma A2. Okay, that's what that means. Oops. If you have a vector B, you're going to call it B1, comma B2. Because we know that we're talking about vectors in the plane. Every single vector defines a point. You might not know what point that is, but guess what? It has 2 coordinates, right? And so give them names. Well, since that's called A, why don't we call this A1 and A2? Since that's called B, why don't we call this B1 and B2? And the rule is that you just take the first component, add them, you take the second components, and add them. Okay? So this is the definition. Definition of vector addition. Okay? That's how we're going to define it. So we can add vectors. What else can we do with vectors? Well, what?
Multiply.
Not quite.
No.
Not quite. You can multiply 2 vectors together, though there are more than one ways of doing that. You might think, well, you just multiply the same way, right? You just take component-wise and multiply it. We don't do that.
Well,
It messes up the geometry.
don't you add the one and multiply the other? Like you add the modulus and multiply it, or
There's
something.
but that's with complex numbers, which are different from vectors. They're subtly different because complex numbers have that I, and that I, the rule of multiplication with I, changes things. Vectors don't have that. Vectors are a bit more general. They say we're not going to deal with that I stuff. We're going to do this, and so we will talk about a way of multiplying a vector together. We don't call it that, or multiplying 2 vectors together. There's something that can be, there's what we call a product. But you see, the thing is, with 2 vectors, you have both an inner product and an outer product. Well, okay. And so, because there's more than one way of doing it. So things get a bit more complicated. But what we can do is we can take a vector and multiply it by a scalar. And the rules for that are as follows. Need some more space. Give me just a second. But so not the next time we meet, so probably Thursday, we're going to talk about the inner product of vectors. I mean, you could think about it as multiplying vectors, though nobody ever calls it that. You're not really multiplying vectors because, as you'll see, it doesn't really behave like multiplication does. Multiplication of 2 numbers gives you back another number. Multiplication of 2 vectors doesn't give you back a vector. Right? Now we could, if you wanted to, just define it the same way. So why don't you just do it, where you multiply vectors by multiplying the components together. You could do that. That's perfectly good. And you'd be the only person who's done that. Like, you'd be off in your corner doing it by yourself, and nobody else is doing it. Okay, cool. It's just one of those things that we don't really do, because it turns out to not be very useful for what we're talking about here. Just the way it is. Inner products and outer products turn out to be very, very, very useful. But another thing we could do is we can multiply a vector by a scalar. And so, if m is a scalar and v is a vector, then mv is the same thing as m times what am I going to put in here? What comma what?
V1 and V2.
Right, okay, thank you. V1, V2. The rule is that you just multiply each one of these. M times V1, M times V2.
So it's just like distribution.
There you go. You could say that scalar multiplication distributes into a vector. And this actually does make some sense, because remember how when we first thought about this geometrically, right? We had, let's say, 2 coordinates. Oh, I don't know. Let's call this one root 3 and let's call this one 1. And that would make this length here 2.
Yeah.
Right? And so, well, let's just call that vector u. Now let's see what happens when I multiply u times 2. It should, if I multiply it by 2, then the total bit here should be 4, right? If from here to here is 2, then the new bit, if I multiply it by 2, should give me a total of 4. Yeah?
Yeah.
And so u was root 3 comma 1. So then 2u would be 2 times that, would be 2 root 3 comma 2. And so that brings me out to 2 root 3 comma 2. And what's the magnitude of that guy?
It'd be 4.
It better be, right? Now let's just check, right? 2 times root 3, so that's 4 times 3 plus 4 is 12 plus 4, 16.
Root 16.
Indeed, 4. Yeah, it does. And in fact, like I think on day 1 or day 2, we did this in general, right? I had like an A and a B, and I say, because what are we doing? We're scaling triangles, right? If you scale a triangle by any amount, you scale every single component by the same amount.
Yeah.
So, right? So that's all we're doing here, right? You have a vector. In other words, you have a right triangle. And you scale it by some amount. Well, you just scale every single component by that amount. Easy enough, okay? So this rule actually does make some sense. But this is why we're defining it this way. And this is the definition of scalar. Well, no. Is it vector multiplication? Scalar multiplication of a vector. Okay? Everybody got that? Questions? Okay. So, why not? So, notice what happens if you multiply a vector by -1. Okay. So if u, we said, was root 3 comma 1, if I take it and multiply it by -1, and we call that just negative u, that's -1 times root 3, 1, which is just, by the rule, we just bring it in. It distributes into the vector -3, -1. Well, -3, -1, the brief right there, right? It just flips it. It flips it. It reflects it through the origin, right? So if v were, say, -1 comma 2, that's v. Is -1 comma 2, then negative v would be -1 times that. -1 comes in, makes that guy positive. -1 comes in, makes that guy negative. And what does he do? Well, he goes now 1, -2, just like that, right? Same magnitude, right? The magnitude hasn't changed. You're going to get the same thing, okay? But he's just flipped direction through the origin. Okay, so everybody got this so far?
Yes.
Okay, we're almost done. So we did -a. There's one more vector that you need to know, one more very important vector. It's the 0 vector, and we write it with a 0 with a little arrow over it. Can you guess what its entries are?
0, 1, 0, 0, 1, and 0,
0, 0.
So just the origin.
It's just the origin. It's the vector whose tip and tail are the same.
So it's just a dot.
It's a dot. Yep.
Oh.
But remember, as like when we were talking about adding, you had to have an additive identity. in order to have, well, in this case, a field or whatever. Although vectors don't form a field, but it's real. It may seem trivial, but we use 0 all the time, right? And it's really important that we have the number 0. In fact, it was like mankind went on a different route once they're like, what if 0's a number? And then like things just completely change. Same kind of thing here. You want an additive identity. You want to treat it as its own thing. In this case, you want a vector that when you add other vectors to, you get the 0 vector. Okay? So like, for instance, if I take v and negative v and add them together, what do I get?
0.
V plus negative v, oops, would be the same thing as negative 1 comma 2 plus 1 comma negative 2. And so by our rules, we add those together. Negative 1 and 1 give me 0. 2 and negative 2 give me 0. And so it gives you the 0 vector.
Wait, but how could the 0 vector be a vector? Because it has no direction.
Good question. It's true. It doesn't have a direction. In fact, it has every direction.
A direction of 0.
So it's one of those cases. It's kind of like, well, you could, one thing I didn't say about fields was that every element has a multiplicative inverse. Well, every element except for 0. So it's one of those, this is another one of those things. It's like every vector has a magnitude and direction except for 0, right? It's one of those that just stands out. And it's just, that's the way it is. But you need to have it. Otherwise, you've just added 2 vectors together and then you didn't get a vector. Now, we need to have it so that no matter what 2 vectors you add together, you get a new vector. Even if it's 0, 0, it's that. So yes, that is kind of where the definition breaks down, in that it has a magnitude and direction. The 0 vector has neither magnitude nor direction, right? So it's like, is that, well, we just kind of say, well, we'll just call it a vector. That way, we have something. That way we could say we have closure. So that I add 2 vectors together and I always get a vector.
Yeah.
Because it could be the case, well, I added 2 vectors together and now I'd have this thing that has no length and no direction. It's like, yeah, sorry. Okay, so I know we're running late, but I got to tell you guys how to do your homework. So, that little pink box, it's going to have all of this stuff on it. I'm going to go ahead and write it all down right now.
It's 1 through 9 odd, right?
No,
Or every
it's every single one. Every single one. All of them. All of them. I'm going to write all of them down right now, and then I'm going to prove one of them for you. So this is the properties of addition and scalar multiplication for vectors. And throughout, n and m will be scalars, real numbers. Okay? 1. We already did this. You will prove that. 2. A plus B plus C equals A plus B plus C. 3. A plus the 0 vector equals what?
A.
It had better, and you will prove that. 4. A plus negative A is equal to
0 vector.
the 0 vector. 5. M, which we know is a scalar, m times A plus B is equal to, any guesses?
MA plus A.
Yeah. And you will prove that. 6. M plus N times A. Any guesses?
MA plus NA.
That's right. 7. This one's stupid. Mn times A is equal to M times NA, which is equal to N times MA. Again, these are they're very, and you'll see, when we're going to prove the hardest one, which is this. number 2. I still want you to write it up. We're proving it in class, but I still want you to write it up. 1 times A
Equals
is A. And finally, notice this is the scalar 0.
Oh.
The scalar 0 times A is equal to 0 vector, which is then equal to any m times the 0 vector. So what I'm looking for here. Now pay close attention. I'm going to say something, and I want you to listen to it. Your book does a couple of these. I don't want you to do it the way the book does, because the book skips a step as far as I'm concerned. I don't want you to skip the step. I will show you what the step is, and you had better not skip it, okay? You do it the way Justin does it. You do it the way Mr. Thompson does it, not the way the book does it. So we're going to do 2, okay? And I'm proving an equation. What am I going to start with?
One side.
Only one side of the equation. So I'm going to choose one. How about this one? So this is 2. I'm proving 2. I'm going to start with this. A plus B plus C. Now, this is the step I want you to do that your book does not. You go from this into equals, now we're going to write it as A1, A2 plus B1, B2 plus C1, C2. They skip this step and go right into the very next step. I don't want to see that. That's sloppy. I want, and this will also reinforce to you, like, that these are the same things. That's the same thing. These are interchangeable, okay? And they're always interchangeable. Whenever you're doing work from here on out, you can at any time go through and change them out, okay? Okay? So now, what these parentheses mean is you do that one first, okay? So that's what we're doing. We're going to do that one first. I'm leaving this alone, A1, A2. And so that's like going to be important here, right? That you do what's in the parentheses first. I guess that doesn't, well, that's not that. But like here, right? Well, I mean, like I said, that one's just bad. Anyway, but here's the idea, right? So now I'm going to drop parentheses and actually do that. So what is that? It's what comma what?
B1, C1.
B1 times C1?
No,
Plus
no.
There you go.
Yeah.
And then
B2 plus C2.
now we could add these. And that gives me, what does that give me?
A1 plus B1 plus C1. A2 plus B2 plus C2.
Okay. Now where are we trying to go? We're trying to go here. So we're going to need to peel off a C, it looks like. Can we peel off a C? Well, yeah. That's what this would have been if we hadn't have added the C in, right? I mean, it's the same kind of thing here. Only instead of the A's, we just pull the C's off. Okay, so there's A1 plus B1, comma, A2 plus B2. Like that. And then this guy is indeed what you would have gotten if you had done this. And the whole time I'm doing this, right, I'm looking ahead as to what does my final thing need to be? How do I get closer to that? Well, that's what this would be. A1, A2 plus B1, B2. Like that. And now, again, the book doesn't do this. I want you to do this step where you say, that's the same thing as A. That's the same thing as B. That's the same thing as C. And now you're done. Okay? So really you're just using definitions of everything that we've talked about thus far. And I wanted to say something. Yeah. So every one of these. I want to see little proofs for every one of these. Just like this. Okay? And something else I wanted to say. It's not coming to me. Any questions?
I don't think so.
Oh, okay. Let me give you